All right, get ready to dive deep because today we're going on a journey into the mind of Ludwig Boltzmann.
Oh, yeah, a giant of 19th century physics.
Exactly, and we're talking about his quest to explain thermodynamics using the idea of atoms. Like, how do you explain heat with these tiny invisible things?
A real head scratcher. It's like
Yeah,
bridging that gap between the invisible world of atoms and what we actually experience, right?
absolutely. It's a philosophical puzzle, too.
Yeah.
And our guide for this deep dive is, well, the Stanford Encyclopedia of Philosophy.
Rice.
Their entry on Boltzmann's work in statistical physics, to be precise. So what we're going to do is track how Boltzmann's ideas evolved. Look for those aha moments, those shifts in his thinking that show both the power and, the challenges of explaining the universe with these tiny particles.
And it's especially fascinating because back then, the very idea of atoms was still up for debate.
Right, like, do they even exist?
Exactly. So he was a real pioneer, forging a path into this uncharted territory.
Okay, so let's start with early Boltzmann, somewhere between 1866 and 1871. What was he wrestling with during this time?
Well, he was trying to tackle the second law of thermodynamics head on. He wanted to prove it, but directly from the laws of mechanics, without even bringing probability into the picture.
Wow, ambitious much.
Yeah, super ambitious.
But, for those of us who might need a little refresher, what exactly is the second law of thermodynamics again?
Basically, it says that entropy, think of it like disorder, always increases in a closed system.
Huh.
Explains why heat goes from hot to cold, why you can't unscramble an egg. Things tend to go towards more disorder.
Right, right. It always seems like things are getting messier, never the other way around.
Exactly.
So Boltzmann was basically saying, hey, this law, this increasing disorder, can be explained just by how atoms move, like a purely mechanical explanation.
Precisely.
But here's the thing. Wasn't he already influenced by James Clerk Maxwell's work? The guy who brought probability into the study of gases?
Oh, absolutely. That's where things get really interesting. On one hand, you have this deterministic view, right? And then probability starts creeping in on the other side.
So it's like this battle in his mind, deterministic versus probabilistic.
Exactly. And what's fascinating is he didn't just settle on one single way to think about probability. Sometimes it was a time average, like how much time a particle spends in a certain state. Other times it was like a snapshot, the proportion of particles in a specific state at a given moment.
A lot of different ways to slice it.
They even played around with early ideas of like ensemble averages, thinking about a bunch of similar systems all at once.
Like a whole collection of them, not just one.
Right. So you can see he was grappling with the very meaning of probability, what it meant in the context of these systems of particles.
Trying to pin it down.
Absolutely. And this struggle to define and use probability, it pops up again and again throughout his work. It's a theme, for sure.
Okay, but even with all this going on, he was still making some pretty big leaps. He developed something called the Stoßzahlenansatz.
The SEA.
Yeah, it sounds intimidating, but it's basically about collisions, right?
It is. It's all about the rate of collisions between particles in a gas. And the SEA, it assumes that these collisions are random and independent. Like one collision doesn't affect the next. And this let him show that the Maxwell distribution, that bell curve describing how fast molecules are moving in a gas, it wouldn't change over time.
So a pretty basic assumption about collisions leads to, like, this stable property of the gas.
A seemingly simple assumption, but big implications for understanding equilibrium.
Okay, but I have a feeling this SCA is going to come back to bite him later on.
Right. Yeah, you're catching on quick. Yeah, it's going to be a major player in some of the big controversies that his work is going to spark. But before we get to all that drama, we got to talk about another big idea Boltzmann was working with. The ergodic hypothesis.
Ooh, ergodic hypothesis. Now that sounds like something straight out of philosophy class. What's that all about?
Imagine a billiard ball, right, on a perfectly smooth pool table, moving forever without any friction.
Okay, got it. Frictionless forever.
The ergodic hypothesis basically says that this ball, given enough time, will visit every single point on that table.
Interesting. But how does a billiard ball, connect to atoms and thermodynamics? Seems like a jump.
Well, Boltzmann saw a connection. He thought maybe this ergodic idea could apply to gas molecules, too.
Okay.
Saying that over a really long time, a molecule would explore every single position and speed it could, while still conserving energy. And he was trying to link this mechanical picture, the billiard ball moving around, to the idea of a system reaching equilibrium.
Ah, I see. So the ergodic hypothesis is like a bridge between like the randomness of how individual particles move and the predictable, stable behavior of the whole gas.
Precisely. It's like trying to find the hidden order in the chaos.
Exactly.
But even early on, he had his doubts about whether this ergodic hypothesis actually held true for real systems.
So some skepticism right from the beginning.
Yeah, it wasn't a sure thing for him. He went back and forth on it throughout his career, sometimes accepting it, sometimes rejecting it. It was a struggle.
So even in these early years, we can see the beginnings of the debates and controversies that are going to follow him. Probability, determinism, even just like the very foundation of how we connect the tiny world of atoms to the bigger world we see.
Oh, yeah. And things are going to get even more interesting as we move into the next phase of his work. He's going to come up with groundbreaking ideas, face intense criticism, and ultimately change how we understand how probability shapes, well, everything.
Okay, so we've got Boltzmann wrestling with these big ideas, probability determinism, trying to connect the world of atoms to the laws of thermodynamics. What happens next in this whole saga?
Well, get ready because things are about to get, well, pretty heated. This period from 1872 to 1877, it's a time of both huge triumph and real turmoil for him. He publishes some of his most important work, but also faces a ton of criticism.
Oh, I love a good scientific showdown. Tell me more. What did he come up with that caused such a stir?
So in 1872, he publishes this paper, and it introduces two really key innovations: the Boltzmann equation and the H theorem. The Boltzmann equation, it's a pretty complicated mathematical formula, and it basically describes how the distribution of velocities in a gas, how fast the molecules are moving, changes over time because of all those collisions.
Okay, that sounds pretty technical. When we break it down a little,
Yeah.
what's the significance of this Boltzmann equation?
Think of it as a way to track how a gas goes towards equilibrium. It starts off all jumbled up, and then it settles into a more stable state. The equation shows how that happens.
So it's a way to describe how even a chaotic system can become more predictable over time.
Exactly. It's like a bridge between those random collisions happening all the time and the overall properties of the gas that we can actually measure.
Okay, I'm starting to get it. But you mentioned the H theorem, and you said that caused a lot of controversy. What's so controversial about that?
Well, Boltzmann defined this quantity, H, and it's mathematically connected to the entropy of the gas. Remember, entropy is like disorder. The H theorem states that for an isolated system, this H value will always decrease over time.
So less H means more entropy, more disorder.
Right. And since H is linked to entropy, a decreasing H means, well, increasing entropy. And that's where the controversy comes in.
So is he basically saying the H theorem proves the second law that entropy always increases?
That's exactly how he saw it. He was like, boom, I've found a way to derive the second law from how particles move.
A pretty bold claim.
It was, and this is where the problems start. The H theorem, as Boltzmann formulated it, it only really works for a specific kind of system. It's got to be a gas where the molecules are pretty spread out, and they only interact through those quick, bouncy collisions like billiard balls. And remember the SCA, that assumption about collisions being random? Well, that's built into the H theorem, and it's not always going to be true.
Right, so he's taken a very specific case and tried to make it into a general rule.
You got it. And he doesn't seem to fully realize the limitations of his proof at this point. He's really confident, maybe a little too confident, that the H theorem is universal.
So he's riding high, thinking he's cracked the code, but there are cracks starting to show.
And those cracks, well, they get exposed by one of Boltzmann's own colleagues and friends, Joseph Loschmidt.
Uh-oh, sounds like a friendship testing moment. What did Loschmidt do?
He comes up with what we now call the reversibility objection. It was a really devastating critique of the H theorem.
Okay, I'm all ears. How does he challenge the H theorem?
Imagine a system, right? Some gas molecules doing their thing. The H theorem says entropy is increasing. Now imagine you suddenly reverse the direction of every single molecule.
Like hitting rewind.
Exactly. And the laws of mechanics, they're time reversible, so this reverse system should also follow the H theorem. But here's the kicker. In this reverse system, H would actually increase, not decrease.
So entropy would be decreasing.
Yeah, which goes against the second law and the whole idea of entropy always increasing.
Wait, so reversing time breaks the H theorem. That's a pretty big problem.
Huge problem. Loschmidt's point was, hey, if the H theorem can be violated by just reversing time, it can't be a universal law.
So Boltzmann's supposedly airtight proof of the second law just got blown wide open. How did he take it?
His initial response, pretty weak. He basically said, oh, those reverse states where entropy decreases, they're just too unlikely. Don't worry about them.
Not very convincing.
A lot of physicists, including Loschmidt, they weren't buying it. They saw it as a major blow to the H theorem and Boltzmann's whole attempt to explain the second law with just mechanics.
So what happens next? Does Boltzmann admit defeat, or does he fight back?
Well, Boltzmann was brilliant, but also stubborn. He wasn't giving up that easily. This whole challenge forced him to completely rethink his approach, and what he came up with, well, it's a revolution in how we understand probability and thermodynamics. But that's a story for the next part of our deep dive.
So Loschmidt has just thrown this huge wrench into Boltzmann's whole idea of proving the second law. Does he just give up, or does he find some way to, rescue his ideas?
Well, this is where Boltzmann's, real genius shines through. Instead of backing down, he totally rethinks his whole approach. And this is a big turning point. It's really the birth of what we call statistical mechanics.
Okay, now I'm really intrigued. So what is this new perspective he comes up with?
He shifts from focusing on, the exact path of each individual particle to looking at the overall state of the whole system. It's not about tracking every single collision anymore. It's about probabilities and possibilities.
So instead of all the nitty-gritty mechanical details, he embraces the randomness of it all.
Yeah, exactly. It's a massive shift in how he's thinking about things. And in 1877, he publishes this paper on the relation, where he lays out this new approach, this combinatorial approach. And he introduces these ideas of microstates and macrostates.
Microstates and macrostates. Okay, those sound like some important terms. Can you, break those down for us?
Sure. Imagine a container full of gas. A microstate is a super detailed description of that gas at a particular moment, where each and every molecule is, how fast it's moving, all of that.
Okay, so it's like a snapshot of the system, but super detailed.
Yeah, right down to the position and momentum of every single particle. Now, a macrostate, that describes the big picture stuff, like temperature, pressure, volume, things like that. It doesn't care about the exact arrangement of the individual molecules, just the overall properties that you could measure.
So the macro state is like a summary, the overall picture.
Exactly. And here's the key insight, the connection to probability. Boltzmann realized there could be tons of different microstates that all give you the same macrostate. You can shuffle those gas molecules around in a zillion different ways, and the temperature, pressure, volume, they all say the same.
So the macro state is like a category, and there are lots of different microstates that all fit into that category.
Exactly. And that's where the probability comes in. The more microstates that lead to a particular macrostate, the more probable that macrostate is. It's kind of like if you flip a coin 1,000 times, you're way more likely to get close to 500 heads and 500 tails rather than 900 heads and 100 tails. There are just more ways to arrange the coin flips to get that 50-50 split.
That makes sense. So Boltzmann's saying the most probable states, the macrostates, are the ones with the most possible microstates.
Bingo. And guess what? The macrostate with the most microstates, the most probable one, it corresponds to the Maxwell distribution, the equilibrium state.
So he's saying equilibrium is the most likely because there are just so many ways to arrange the particles to get that state. The system is naturally drawn to the state with the most possibilities?
That's the idea. And this was a huge breakthrough. It gave everyone a whole new way to understand why systems tend towards equilibrium. It's not some mysterious force pushing them there. It's just statistics. It's the most probable outcome.
This whole approach, this combinatorial approach, it seems like it sidesteps that whole reversibility problem that Loschmidt brought up, right? He's not focusing on the specific paths of the particles anymore, just the overall probabilities.
You're right. It does address that reversibility issue in a really clever way. Even if you could reverse the velocities of all the particles, the system is still overwhelmingly likely to end up in one of those macrostates with a huge number of microstates.
Yeah.
So it'll still tend towards equilibrium. The reverse state, yeah, it's possible, but it's super unlikely.
So Boltzmann's new approach isn't just elegant, it's also it holds up against those criticisms.
It does, and it really shows how he could adapt and refine his ideas when challenged. He took this seemingly fatal objection and turned it into a chance to develop a much deeper understanding of thermodynamics.
But did this new approach completely shut down his critics? Was everyone convinced?
Well, not everyone, not entirely. There were still some people who questioned the basis of his ideas, like that ergodic hypothesis, remember? He kept coming back to that, and it was still a point of debate. And he faced some new challenges too, like Zermelo's recurrence objection, which suggested that even statistically, systems should eventually go back to their starting state, which seems to contradict the whole idea of entropy always increasing.
So even with this breakthrough, there was still more work to be done, more questions to answer.
Absolutely. Boltzmann's journey wasn't over. He kept wrestling with these fundamental questions, probability, determinism, even the nature of time itself. But what he did, it laid the foundation for statistical mechanics. And that's become essential to how we understand all sorts of things, from how gases behave to, like, the evolution of the entire universe.
It's amazing to think that all of these deep ideas about probability, entropy, even reality itself, they all came from Boltzmann trying to understand the world of atoms. He really was a pioneer.
He was. He pushed the boundaries of what we knew, and he left us with a lot of deep, thought-provoking questions that are still relevant today.
This has been a wild ride. It really makes you think. Thanks for guiding us through this deep dive into Boltzmann's work.
It's been a pleasure. Always happy to explore the mind of a scientific giant.
Well, it's definitely been a mind-bending experience. And that's it for our deep dive into the world of Boltzmann's statistical physics. We'll see you next time for another deep dive into the world of ideas.